Section: Introduction. In this section, we explore how the thinking skills of very large language models, also known as LLMs, are getting better. This improvement is evident from their performance on a wide range of challenging tasks in mathematics, science, and computer programming. At the same time, techniques like reinforcement learning from human feedback, RLHF, and specific fine-tuning methods have made significant strides in making these models act more in line with what humans prefer. By teaching these models how to follow instructions more effectively, we've managed to unlock more complex behaviors simply by asking them in the right way. This has led to the development of advanced strategies to enhance the reasoning abilities of LLMs, such as the chain of thought and tree of thought methods. Looking back, reinforcement learning, RL, has been used to train neural networks to plan and reason in complex game environments, with notable successes including AlphaGo, AlphaStar, and OpenAI's Dota 2 project. A standout example is Cicero, which combines an RL-trained planning agent with a dialogue-enhanced LLM to achieve almost superhuman performance in the board game Diplomacy. Given these achievements and the interactive nature of problem-solving, it seems like a natural progression to apply RL to enhance the reasoning capabilities of LLMs. In our study, we investigate how RL concepts can be applied to LLMs to improve their reasoning across various reward systems and starting points. We begin by evaluating the effectiveness of different RL algorithms on reasoning tasks, which are essentially sets of question-answer pairs. These tasks are extended to define a Markov decision process, where tokens act as both actions and the evolving state, with the process following a set pattern. We experiment with different types of rewards, including a simple reward for correct final answers, rewards for matching steps in a reference solution, and rewards generated using a model. We assess models with 7 billion and 13 billion parameters, starting from both supervised fine-tuned checkpoints and pre-trained checkpoints. We measure performance using 4 metrics: the majority score when sampling once per question, the majority score when sampling 96 times per question, a re-ranking score based on sampling 96 times and using a model to pick the best answer, and a pass score based on sampling 96 times and comparing to the correct answer. Our findings reveal that, surprisingly, the simplest method, expert iteration, often outperforms more complex algorithms across most metrics and setups. Even more, expert iteration and proximal policy optimization, a more sophisticated approach, require a similar number of samples to reach their best performance when starting from a pre-trained model. We also notice that the performance gap between pre-trained models and those fine-tuned with supervision narrows significantly after RL fine-tuning, especially with larger models. Previous studies have shown a trade-off between performance on immediate answers and the pass score during supervised fine-tuning. We pinpoint the limited diversity of the dataset as a key reason for this. Our results show that RL fine-tuning can improve both metrics simultaneously, thanks to its ability to generate a more diverse set of training examples. We discuss why expert iteration and return-conditioned RL are competitive with proximal policy optimization, highlighting 2 main reasons. First, the reasoning tasks we look at have deterministic dynamics, a scenario where direct behavior cloning and return-conditioned RL excel. Second, we identify a lack of sophisticated exploration by models during RL fine-tuning as a limiting factor, which affects the performance advantages that proximal policy optimization might have. We conclude by discussing the implications of our findings for RLHF and the future of fine-tuning LLMs with RL. In summary, our contributions include a comprehensive study of fine-tuning LLMs on reasoning tasks using different rewards, model sizes, and starting points, a comparison of expert iteration and return-conditioned RL, showing that expert iteration consistently achieves the best performance, and a discussion on the implications of our findings for the future of RL fine-tuning for LLMs, highlighting exploration as a major challenge. Section Summary. In this section, we explore how reinforcement learning, RL, techniques can enhance the reasoning abilities of large language models, LLMs, across various reward schemes and model initializations. By comparing different RL algorithms on reasoning tasks, we find that expert iteration A outperforms other methods, showing competitive sample efficiency and performance. Our study highlights the potential of RL fine-tuning to simultaneously improve both test time performance metrics, addressing limitations in supervised fine-tuning and emphasizing the importance of exploration in enhancing LLM reasoning capabilities. Section: Methods. In this section, we delve into how we approach the challenge of enhancing the reasoning capabilities of large language models, LLMs, through reinforcement learning, RL. We explore the effectiveness and the necessary amount of training data for different RL strategies, specifically focusing on expert iteration, A, proximal policy optimization, PPO, and return-conditioned RL, RCRL. Our main objective across these methods is to maximize the expected future rewards that a policy can achieve on a given task. The ultimate goal is to identify or develop the best possible policy, known as the optimal policy. PPO stands out as an online RL method that alternates between exploring various strategies and refining the policy based on the exploration's outcomes. It's unique because it learns from the actions taken directly by the policy it's trying to improve. During the learning phase, PPO updates the policy by estimating the advantage, which is the difference between the expected rewards of taking a certain action in a given state versus the expected rewards of being in that state regardless of the action. For practical purposes, we train PPO by sampling a specific number of scenarios, adjusting the model through several training epochs, and selecting the best model based on its performance on a validation set. On the other hand, expert iteration is somewhat similar to PPO in that it's also an online method but leans more towards being off-policy. It starts with an initial guess of the best policy and refines this guess by learning from a mix of exploration and exploitation. This method often involves generating a preliminary set of actions and outcomes, which are then used to improve the policy iteratively. The improvement process involves a standard loss function that measures the difference between the predicted and actual outcomes. In our experiments, we also explore return-conditioned RL, which aims to develop policies that can adjust their actions based on the desired outcome. This method involves training a model to predict the best action to take, given the current state and a specific target outcome. We prepare the training data for this approach by using the best policy we have from expert iteration and labeling the steps based on their likelihood to lead to a correct solution. Additionally, we investigate the use of outcome-based reward models, ORMs, as a way to verify and rank different solutions proposed by the models. ORMs are trained to predict the probability of a sequence of steps leading to a correct solution, which helps in selecting the most promising solutions. Throughout this exploration, our aim is to understand the strengths and limitations of each RL method in the context of fine-tuning LLMs for reasoning tasks. By comparing these methods, we hope to identify the most efficient and effective strategies for improving the reasoning abilities of LLMs. Section Summary. In this section, we explore the performance and sample complexity requirements of various RL algorithms like expert iteration, A, proximal policy optimization, PPO, and return-conditioned RL, RCRL, when fine-tuning LLMs on reasoning tasks. Each algorithm aims to find the optimal policy pi** in different ways, with PPO being an online RL algorithm that engages in exploration and policy improvement phases, while expert iteration is more off-policy and involves constructing an initial expert policy approximation before policy improvement. Additionally, return-conditioned RL algorithms train policies conditioned on both the current state and desired return, aiming to learn policies that can adapt based on the desired return, similar to a decision transformer. Section: Experiments. In this section, we delve into the process of evaluating our models on two math word problem benchmarks known as GSM-8K and SVAMP. Additionally, for the GSM-8K benchmark, we explore two different scenarios, one where we have access to SFT, supervised fine-tuning, data, and one where we do not. We assess all models using several metrics: greedy sampling accuracy when considering the top prediction, MAJ at 1, majority vote accuracy across 96 samples, MAJ at 9.6, accuracy after ORM, optimal reward modeling, based re-ranking of 96 samples, re-rank at 96, and the accuracy of the best prediction out of 96 samples, pass at 96. Unless mentioned otherwise, we opt for greedy sampling for MAJ at 1 and use a temperature setting of 0.7 for the other metrics. Our models, which are based on RCRL, reinforcement learning with critical response learning, generate responses one step at a time, taking cues from the good token. While the concept of a step might be vague in general, in our context, we consider a step to conclude with either a sentence or a new line. All our experiments are conducted using models known as Llama 2.7b and Llama 2.13b, which have been fine-tuned with instructions. When we have SFT data available, we start by fine-tuning the Llama 2 models for 4 epochs, using a global batch size of 128 and starting with a learning rate of 2E5, which we gradually decrease to 2E7 following a cosine warm-up schedule. We refer to the models obtained through this process as SFT models. For fine-tuning with PPO, proximal policy optimization, we use these SFT models as our starting point. However, for both EI, expert iteration, and RCRL, we generate data using the SFT models but reset the training to begin from the pre-trained base model. This resetting strategy is crucial for achieving optimal performance, as we have discovered. Our results for both the 7B and 13B models are presented in a table, showing that expert iteration achieves the best performance with a notable improvement in sample complexity. Surprisingly, A models outperform others with MAJ at 1 accuracies of 0.485 and 0.53 for the 7B and 13B models, respectively. The best greedy accuracy for both models is reached after 2 expert iterations, beyond which the performance plateaus, marking a significant improvement of around 7% over the SFT baseline. PPO models, despite their efforts, do not match the performance of A models, with ORM-guided PPO showing the most substantial improvement of about 5% over the SFT baseline. The improvements are consistent across MAJ at 9.6, re-rank at 9.6, and pass at 96 scores. Interestingly, even after additional training on top of the SFT initialization, PPO models maintain competitive re-rank at 96 and pass at 96 scores, which we attribute to the diverse nature of the exploration dataset used for model updates. However, RCRL models lag behind A models despite being trained on A-generated data with a balanced mix of good and bad step labels. This indicates a challenge in learning the distinction between good and bad steps, suggesting that RCRL models struggle to effectively use information from partially correct solutions during training. An analysis on the ratio of positive to negative labels shows that a balanced ratio leads to the poorest performance, with an increase in positive data correlating with better outcomes. We also observe that PPO models reach their peak accuracy after approximately 60,000 rollouts, while A models require significantly more. However, the training duration for both approaches is roughly the same, primarily due to the memory demands of PPO, which result in lower rollout throughput and smaller mini-batch sizes during training. In the SFT scenario, we did not explore reducing the number of samples from 96 per question for A, but we anticipate that a reduction would not adversely affect performance. Our findings further reveal that additional guidance from ORMs or dense rewards has a minimal impact on performance. While ORMs slightly enhance PPO performance and have a negligible effect on A performance, the overall final performance remains unchanged. This suggests that providing dense rewards, whether heuristically or via ORM, does not significantly benefit performance and may even slightly detract from it by encouraging overfitting to exact solutions in the training set, thereby limiting solution diversity. In a closer examination of pass at 96 accuracies, we find that most models of similar size achieve results within 3% of the best outcome, indicating that with sufficient sampling, most models can solve a comparable range of problems. Interestingly, while our best A model initially appears to significantly outperform the SFT checkpoint in pass at 96 accuracy, this discrepancy is mainly due to the SFT checkpoint undergoing more extensive training on a less diverse dataset. A moderate amount of supervised fine-tuning can achieve a MAJ at 1 accuracy of 0.36 and a PAS at 96 accuracy of 0.76, suggesting that RL training primarily affects MAJ at 1 accuracy without significantly improving PAS at N accuracy, which can be attained with minimal supervised fine-tuning. The close PAS at 96 accuracies among most models contrast with the re-rank at 96 performance, where A models hold a roughly 5% lead over others. This gap may partly result from the ORM's overfitting to the A model, which was used to generate its training data. Section Summary. In this section, we evaluate our models on 2 math word problem benchmarks, GSM-8K and SVAMP, considering different data regimes and sampling strategies. We find that expert iteration, A, outperforms other methods, achieving a significant improvement over the baseline models in terms of accuracy metrics such as MAJ at 1, MAJ at 9.6, re-rank at 9.6, and PAS at 9.6. Additionally, we observe that reinforcement curriculum learning, RCRL, models struggle to distinguish between good and bad steps, leading to lower performance compared to A models, highlighting the importance of training data diversity and model initialization strategies. Section. Results with no SFT initialization. In this section, we explore what happens when we don't have access to supervised fine-tuning, SFT, data for training our models. Specifically, we look at how models perform on 2 different question sets, SVAMP and GSM-8K, without SFT data. To give our pre-trained models a bit of a head start, we provide them with a 2-shot prompt using examples from the GSM-8K validation set. However, for models using the exploration and iteration A method, we remove these prompts after the first exploration round and instead rely on the data generated through the A process. We continue running both the proximal policy optimization, PPO, and A algorithms until we see no further improvement in performance. For PPO, this point is reached after 250 steps for SVAMP and 1000 steps for GSM-8K. For A, it occurs after 5 rounds of exploration and distillation. Our findings show that even without SFT data, A outperforms other methods on SVAMP, significantly boosting the accuracy of pre-trained models. For instance, the accuracy of 7B, 13B pre-trained greedy models jumps from 0.06, 0.05% to 0.58, 0.69%, respectively. On GSM-8K, PPO slightly outperforms EI, with improvements from 0.05, 0.03% to 0.31, 0.4%. Both algorithms achieve similar scores when it comes to passing at least 96% of the tests, which supports our observation from the SFT data scenario that A mainly enhances the majority vote accuracy compared to PPO. Interestingly, the prompted 13B model on GSM-8K nearly matches the performance of the SFT model, achieving a 0.83 PAS at 96 accuracy without having been trained on SFT data. We also discovered that A and PPO have similar sample complexities, which was unexpected. On GSM-8K, PPO models reach their highest majority vote accuracy after just 30,000 model rollouts, and even fewer on SVAMP. Surprisingly, A models require more samples to converge on SVAMP but achieve much higher accuracy. On GSM-8K, A seems to have a higher sample complexity, likely due to oversampling each prompt during exploration. To address this, we reduced the number of samples per prompt in each A round from 96 to 4. This adjustment made A models require more iterations to converge but significantly reduced the total number of samples needed, achieving nearly the same accuracy with far fewer samples. This finding is particularly interesting when comparing the performance of A and PPO on traditional reinforcement learning problems, where PPO usually requires fewer samples. Regarding implementation details, we found that reinforcement learning, RL, training can be quite sensitive to the architecture and hyperparameters chosen, especially for fine-tuning large language models, LLMs. For our PPO models, We used a joint architecture for the policy and value heads to save memory, with a relatively large value branch and detached gradients to prevent interference between value and policy gradients. Low rank adaptation with a rank of 128 and a large enough batch size, along with a small learning rate, significantly helped stabilize training. We also experimented with fine-tuning only the top layers of the model, which saved memory but slightly reduced performance. A non-trivial Kullback-Leibler (KL) penalty was critical to prevent model collapse, especially given the unnatural distribution of text in our reasoning tasks. We also found that sampling parameters greatly affect exploration. The best temperature for exploration depends on whether we're starting from an SFT checkpoint or a pre-trained prompted model. For A, we settled on a temperature of 1.0 to maximize solution diversity without too many degenerate solutions. We experimented with different sampling strategies to promote solution diversity during PPO training but found that setting both K and N to 4 worked best. Lastly, we observed that the quality of the student model's initialization and its size significantly influenced the type of exploration during training. Larger models engaged in more diverse exploration, which directly impacted their performance when trained on exploration data. To further investigate overfitting, we fine-tuned a Llama 2-7B model for half as many steps as the SFT model and found that despite the reduced training time, the model achieved similar or better performance, suggesting that RL fine-tuning might be less prone to overfitting compared to static SFT fine-tuning. This is supported by the improved diversity and accuracy of solutions generated by models undergoing RL fine-tuning.